Good morning, students. We are learning computer arithmetic, and we have seen addition and subtraction of signed magnitude data, right? So here, signed magnitude data is different from 2's complement representation of the data. That we have learned how the signed magnitude data is represented. Separate bit for sign is used, correct? In sign magnitude representation. And we also saw how this addition and subtraction is performed with the circuit diagram. And also we saw the flow chart, right? How the flow of the process happens. So before starting, today we are going to learn about the addition and subtraction of 2's complement representation. Okay. So before starting this, you should be clear with how data is represented in signed magnitude representation and how it is different. Okay. How signed 2's complement representation is different from this. Here, as I told you, in signed magnitude representation, the numbers are if the number is represented using a 4-bit binary, okay, the first bit, let's say 0, 0, 0, 0, it is 0. But the fourth bit, if there are 4 bits, the fourth bit is used for representing the sign. If it is 0, it is positive, the number is positive, and if it is 1, it is negative. So this bit is the fourth bit. If there are n bits, the nth bit is entirely for representing the sign of the number. So here we say this is plus 0, correct? And plus 7, we have also performed arithmetic operations. Plus 7 is 0, 1, 1, 1. This is plus 7. And minus 7 is represented as, we just change the sign bit and the other bits are the same. So this is minus 7, where here the sign bit is 1. And whereas in this positive number, the sign bit is 0. This only differentiate the positive and negative number. Okay, but here in this in the 2's complement representation, it is different. Okay, so here let's first see how signed magnitude representation of this number is done. Zero, 0, 0, 0 represents positive 0. 0, 0, 0, 1 is plus 1. 1, 0. I want you people to write it. Everybody take a note and write this down. Note this down, so it will be helpful when we now perform the arithmetic operations, okay, on 2's complement data. So please write it down. 0, 0, 1, 0 is plus 2. 0, 0, 1, 1 is plus 3. And 0, 1, 0, 0 is plus 4. 0, 1, 0, 1 again is plus 5. 0, 1, 1, 0 is plus 6. And 0, 1, 1, 1 is plus 7. And if you take the other numbers, the next number is after in the series, okay, in this pattern, what is the next number? It is 1, 0, 0, 0. So let me write it here. 1, 0, 0 is, it's not 8. In signed magnitude representation, see the bit position is like this: 2 power 0, 2 power 1, 2 power 2, and this is the sign bit, okay? As the last bit is the sign bit. This is only for, this will not be included as a data. Here the data is represented by only these 3 bits. When there are n bits, only n minus 1 bits represent the data, correct? So 0, 0, 0 is plus 0, 0, 0, 1 is plus 1. As the sign bit is 0, we say it is plus 1. And here it is 2 power 0, 2 power 1, and 2 power 2. So this only designates the data. And this is the sign bit. So we will not consider the sign bit with the magnitude. So we say that this is minus 0. Okay. And 1, the next pattern is 1 0 0 1 is minus 1. 1 0 1 0 is minus 2. 1 0 1 1 is minus 3. 1 1 0 0 is minus 4. 1 1 0 1 is minus 5. 1 1 1 0 is minus 6. 1 1 1 1 is minus 7. Okay, so if you see this representation, the numbers that can be represented, the range of numbers, right, that can be represented using this signed magnitude representation is from minus 7 to 0 to plus 7, correct? Here from minus 7 to 0 and to plus 7. And if you see this, hope this is clear, this is signed magnitude representation. We used AS as the register for storing the sign bit, and A as the register for storing the data bit, and BS as the sign bit and B as the data. So because sign bits need to be treated separately in sign magnitude representation. Now, how signed 2's complement representation is done. Because it is signed, the sign bit will have a sign bit. The fourth bit is when there are n bits, okay, to represent the data. The nth bit is here also is a sign bit. But the difference is the sign bit is not treated separately. Okay, the sign bit is treated with the data bits. Okay, with the magnitude. So here, if you see 0 0 0 0 represents plus 0. 0 0 0 1 is plus 1. 0 0 1 0 is plus 2. 0 0 1 1 is plus 3. 0 1 0 0 is plus 4. 0 1 0 1 is plus 5. 1 1 0 plus 6. 0 1 1 1 is plus 7. Here the representation is the position, if you see 2 power 0, 2 power 1, 2 power 2, and the fourth bit, as the fourth bit is a sign bit, we give a negative sign for this position, 2 minus 2 power 3. Okay, so if you see this, the decimal representation, here all zeros, so when it is multiplied you get 0. Here it is 1 into 2 power 0, which is 1, and here the second position we have 1. So 1 into 2 power 1 is 2. And here 1 into 2 power 1 plus 1 into 2 power 0. So 2 plus 1 is 3. Okay, this way. So how the next number will be, what will be the next number? It is 1, 0, 0, 0. After this, the pattern follows like this, 1, 0, 0, 0. It is 2 power 0, 2 power 1, 2 power 2, minus 2 power 3. Okay, it is signed 2's complement representation. So it is the position at the for the sign bit is minus 2 power 3. So what is this number now? Minus 1 into minus 2 power 3. It is minus 8. Okay, it is not plus 8 as the sign bit is 1 here. Okay, the position is here. If you see, we don't give position, right? Because it is a sign bit, it has to be treated as a separate bit. Okay, just decide the sign magnitude representation. Here, this one is just to decide whether the number is positive or negative. But the other bits decides the data. So 0, 0, 0 is 0. And here, this is treated with the magnitude. Okay. Here we multiply. To find the number, we multiply. Here the position given is minus 2 power 3 as it is a sign bit. Okay, so it is minus 8. And next one, 0, 1, 0, 0, 1. It is minus 8 plus 1, that is minus 7. Okay, 1 0 1 0 minus 6, 1 0 1 1 is minus 5, 1 1 0 0 is minus 4, 1 1 0 1 is minus 3, 1 1, 1, 0 is minus 2, and the last number 1, 1, 1, 1 is minus 1. Okay, so here the least number that is represented is minus 8. Okay, and the maximum number is plus 7. Okay, so here when you represent, that is why signed magnitude representation, performing addition and subtraction using signed magnitude representation is difficult. Okay, if you see this, the magnitude 0, 0, 0 represents 0, and again here another, the same number is represented twice, right? 0, 0, 0. Only the sign bit differs the numbers. Okay, so there are, for every number, there are two representations in sign bit. If you take 4, it is 1, 0, 0, and here also it is 1, 0, 0. Okay, but it is plus 4 as the sign bit is 0, and as just the sign bit is 1, here we okay, the decimal representation is minus 4. But here, whereas you see this plus 4 and minus 4 is different. You can also note that this plus 4, if you take the 2's complement of this number, okay, what you will get? The number is 0, 1, 0, 0. 1's complement is, tell me the 1's complement of this number.
1, 0, 1, 1.
Correct, 1, 0, 1, 1. And when you add 1 to this, you get 1, 0, 1, 0, 1, 1. Okay, it is 1, 1, 0, 0, which is this number, 1, 1, 0, 0. Okay, so the 2's complement of plus 4 is minus 4. Okay, this is how the numbers are represented in 2's complement form. Okay, here, so performing addition and subtraction here in with the 2's complement representation is easy. Okay, when you compare to sign magnitude representation, how we did it earlier. Okay, just if there is a negative number to be added or subtracted, we take the 2's complement of it because we need the negative form. Okay, if the number to be added to a number is negative, we can't add it as, as a positive number. We need to get the negative form. So we just take the 2's complement of it and add it, where sign bit is treated with the other bits. We'll not keep it separately. Even in the procedure, the hardware circuit, if you see the flowchart and all, if you see, there won't be a separate AS and BS for storing the sign bits. They are treated with the other bits. So here addition and subtraction with signed is 2's complement data, as I told you. Okay, the bits are treated as other bits of the number. If one example, if we take 12, okay, the binary representation of 12 is 1, 1, 0, 0. And the sign bit I give, it is positive, so it is, this is a sign bit, okay, 0. And how we find the 2's complement of it? We just invert the bits. 1, 0, 0, 1, 1. This is the 1's complement. And the 2's complement is you add 1 to this. 1, 0, 1, 0, 1, 0, 1. Okay, so this is equal to minus 12. And when you perform addition and subtraction, there may be overflow. We also discussed in the earlier class when we learned about sign magnitude, addition and subtraction. Overflow occur when when two n bits are added and the sum occupies, sum need n plus 1 bits. For example, you are adding two 3-bit numbers, 2 and 3. It is not that all the cases when you add two numbers you get overflow. It is not the case. Okay, when you add two numbers, if suppose the sum occupies n plus 1 numbers, we say that there is overflow. When you add 5 and 7, okay, 5 can be represented using 3 bits. And even 7 can be represented using 3 bits. What is 5? It is 101 and 7 is 111. But when you add, it is 12. What is 12? You need 4 bits for representing this 12. It is 1100. Okay. So here there will be overflow definitely. Whereas you add plus 3 and plus 2. 3 is 0, 1, 1. and 2 is 0, 1, 0. When you add these two, 1, yeah, 1, 0, 1. That is equal to plus 5. So now here the result can be represented in 3 bits. Okay, so there will not be an overflow. We don't call this condition an overflow. Here there is no overflow, whereas when you add 5 and 7, there is overflow. The 3-bit register we have, right, that stores 5 and 7. We can't, that register cannot accommodate this 4-bit. Okay, so there will be overflow. We treat the carry we get as overflow there. How to detect an overflow? So when there is an overflow occur, we need to detect it. Then only because the answer will be wrong. What you get here, if you add 1, 1, 0, 1 is 5 and 1, 1, 1 is 7, you need to get 12 actually. It is plus 12, but you will not get 12 here. 1 plus 1 is 1, 0 and 1 plus 1 is 1, 0. Again 1, 1, correct? And it is 0 because it's positive, 0 negative, and this is, sorry, here what is this? Let's add this number. 1 plus 1 is 1, 0. Here is a carry. 1 plus 1 is 1, 0, 1. It is 1, 1, correct? It is a negative number. This says that this result says that this is negative, correct? So the result is you will not get a negative number when you add two positive numbers. Okay, so we say that there is a overflow. Now there is a procedure to detect if there is a overflow or not. Okay, let's see that it is overflow is detected by inspecting the last two carries out of the addition. Okay, what we do is we add two numbers and we see the carries. Okay, we have to note down the carries. So for example, let's add, yeah, let me take the numbers where you will get overflow. Okay, plus 7 and plus 5. Okay, we are adding 7 and 5. So what is plus 5? Plus 7 is 0, 1, 1, 1 and plus 5 is 0, 1, 0, 1. When you add, we have done it already, 0, 1, 0, it is 1, 1 and it is 1 and 0, correct? Now what you have to note here is the carry into the sign bit. This is the carry. This is C0, C1, C2 and C3 and this is C4. Okay, what is C0? Carry 1, the carry that comes to the first bit. Okay, here there is no carry and the carry out of this comes to the, we get it to the second bit, correct? That is C1. Here we have carry C1 is 1 and C2 is 1, C3 is 1. Okay, and when you add these two, 1 plus 0 is 1 and the carry here we have no carry, so that means it is 0. Okay, so C4 is 0. Now what we notice, we have to take this carry C3 and C4 and if these two carries are same, that means there is no overflow. Okay, and if these two carries are different, there is a overflow. Okay, this case, this is 0 and this is 1, so there is a overflow. The carries are not same. So how it is implemented, how it is detected by computer? Here we sent these two bits to an exclusive OR because exclusive OR can detect if the numbers given are same or different, right? The input bits are same, it produces 0. If the input bits are different, it produces 1, the odd function. So we give this to an exclusive OR, the carry C3 and C4. C3 is, C4 is 0 and C3 is 1. It produces 1. So we check the output of this XOR function. If it is 1, that means there is an overflow. Okay, when these carry are same, there will not be an overflow. So the overflow bit has to be sent with the actual result. Okay, so that it can be treated in the right way. even if you take minus 7 and minus 5, okay, when you add these two numbers, what is minus 7? We need to take the complement, right? Minus 7 is, yeah, 7 is 0, 1, 1, 1, and find the complement of it. It is 1, 0, 0, 0. Add 1 to that. This is 1's complement. Add 1 to this, you get 1, 0, 0, 1. So minus 7 is 1, 0, 0, 1. And what is minus 5? 5 is 0, 1, 0, 1. Invert the bits for 1's complement. 1, 0, 1, 0. Add 1 to this, you get 1, 0, 1, 1. So when you add this, the result should be minus 12. Okay, so there will be overflow here. How will we detect it? We add this 1 plus 1 plus 1 is 1, 0. And the carry C1 is 1. 1 plus 1 is again 1, 0. Carry C2 is 1. 1 plus 0 is 1. And here the carry is 0. Okay, C3 is 0 here. This to be noted. And 0 plus 1 is 1, 0. And the carry here is 1. Okay, so now again these two carries are different. C3 and C4 are different. So there is overflow. The result we get is not correct. Okay, what we got, positive 4. It is not correct. And if you take some, let's take some other number where there will not be overflow. Okay, 7 minus 5. Let's subtract these two numbers. To subtract, what we do? First take the first number. Plus 7 is 0, 1, 1, 1. And 5. Right? 5 is 0, 1, 0, 1. But as it is subtraction, it need to be complemented. 5 need to be complemented. Okay. 2's complemented. So it is, already we did it, and it is the 2's complement of 5 is 1, 0, 1, 1. So minus 5. Okay, 7 minus 5. It is, as it is subtraction, we perform the 2's complement of the subtrahend, right? That is the procedure. So when we do this, it is 1, 0, 1, 1, and you add this 1, 0, C1 is 1, the carry 1 is 1. When you add it, it is 1, 1, again it is 1. You add these 3 bits, 1 plus 0, it is 1, 0. The carry C3 is 1 here, 1 plus 1 is 1, 0, and the carry out is 1. Okay, see, this is a carry that is into the, going into the sign bit, and this is a carry that come out of the sign bit. So carry into the sign bit C3 and carry out of the sign bit C4 is compared with an exclusive R. Okay, here if you check with exclusive R, it is correct, right? The signs are same, the carries are same. The C3 is 1 and C4 is 1. So what is the result? The result is correct here. 0, 0, 1, 0 is plus 2. The sign bit is 0. You can note the sign bit, it is positive. Okay, and the magnitude 0, 1, 0. So it is plus 2. Okay, this is how the overflow is detected during this addition and subtraction. Let's see how it is implemented. The 2's complement, addition and subtraction. Okay, so the hardware implementation of 2's complement, addition and subtraction goes like this. We take the two numbers A in AC. Okay, AC is the register that hold the number A. There is no sign bit, separate sign bit here, as we used in signed magnitude representation, because their sign bits are treated separately. We had a register called AS and BS. Okay, we will not have that here. So AC is the register that hold the value of A, and B is the register that hold B. Okay, and here the procedure is very simple. If it is addition, the process may be, we will not be checking the sign bit as we did for signed magnitude. Okay, directly the numbers will be added if it is addition. Okay, we'll have to separate circuits for addition and subtraction. So here, yeah, if it is addition, the bits are added. B is directly sent to the parallel adder. We saw this circuit, right? In detail, I have explained in the first class. with the signed magnitude representation. So we don't have to look at that again. So here complementer, first A and B will be added for addition. If it is subtraction, what we do? B is complemented. The second, that is subtrahend, is complemented and added to AC. Okay, and when the overflow will be stored in the register B. Okay, the two numbers are taken in AC, register AC and register B. Okay, the operation that need to be performed may be addition or subtraction. And addition, if it is addition, the directly B is sent to the parallel adder with AC and it is added. Okay, and if it is subtraction, it is complemented. B is complemented, 2's complemented and added to AC. Okay, using the parallel adder. So here the flow chart is this. For addition, let's see, here is a separately it is given. For addition, AC is the first number and B is the second number. Okay, what you do, you just add AC and B, and the result we are storing in AC, and the overflow. Okay, whatever the overflow comes will be stored in B. Okay, when you add, you may get overflow that gets stored in B. Okay, so the result includes this AC, the actual result. The result may not be correct if there is an overflow. So we need to consider this bit also. Okay. And subtraction, we take the minuend in AC and subtrahend in B. And how we subtract, we make the subtraction simple by complementing the subtrahend and adding it to the first number, right? Minuend. So that's a procedure. AC is equal to AC plus B complement. 1's complement of B plus 1, that is 2's complement. B and the overflow, if overflow occurs, that will be stored in B. So let's take a bigger number now, plus 12. Okay, perform addition. So first 12 plus 9. Okay, how this is performed? The first number is plus 12, and let's take a 8-bit representation. Okay, 8-bit register. Let's consider that we are having a 8-bit register that hold all the bits. So the sign bit will be the 8th bit. This is sign bit. As it is a positive number, I made it 0. And all the other bits I replace with 0 as it is 8-bit register. And 12 is 1, 1, 0, 0. And plus 9. It is a positive number. The sign is 0. And 0, 0, 0, 1, 0, 0, 1. When we add it, 1, 0, 1, 1 plus 1 is 1, 0, 1, 0, 0, 0. The sign is 0 and 0, 0, 1, 0. So how you calculate what this number is? This is 2 power 0, 2 power 1. Here we have 0. We don't have to consider that. 2 power 2, 2 power 3 and 2 power 4. So what is 2 power 4? It is 16 plus 2 power 2 is 4 plus 2 power 0 is 1. That gives us 16 plus 5, 21. It is, the sign bit is positive here, so it is plus 21. Okay, so the result here is correct. When you add 12 plus 9 is 21. Okay, the result we got is correct. And let's do this. 12 minus 9. Okay, the second. So second problem is 12 minus 9 plus 12. Okay, it is 8-bit, in 8-bit it is represented as 0, the sign bit, 0, 0, 0, 1, 1, 0, 0. And it is minus 9. Sorry, it is subtraction, right? plus 9. 12 minus 9, subtraction with the yes, plus 9. It is subtraction. So what we do for subtraction, we take the 2's complement of 9. Okay, 9 is this. We have already written it here. 9 is 0, 0, 0, 0, 1, 0, 0, 1. Find the 1's complement. 1, 1, 1, 1, 0, 1, 1, 0. Add 1 to this. 1, 1, 1, 0, 1, 1, 1, 1. Correct? This is the 2's complement of 9. 1, 1, 1, 1, 0, 1, 1, 1. You add this 1, 1, 1 plus 1 is 0, 1, 0. Here 1, 0. Again 1, 0, 1, 0, 1, 0, 1, 0, and 1. Okay, the sign bit is 0. And what is this number? 2 power 0 and 2 power 1. That is 2 plus 1 is 3. Okay, as the sign bit is 0, it is the sign is plus 3. Okay, what is 12 minus 9? Plus 3. Okay, so here we got the right answer. And let's take another example. Yes, 2 minus 3. Okay, the numbers to be added is subtracted. Okay, it's subtraction. So 2 minus 3. How we represent it? Plus 2 is, let's take, these are 3-bit numbers. Let's take 4 bits. Okay, with the 4th bit as sign bit. 0, 0, 1, 0 is plus 2. And it is subtraction. So 3 need to be complemented now. What is 3? It is 0, 0, 1, 1. Complement the bits. It is 1, 1, 0, 0. 1's complement, add 1 to this, 1, 1, 0, 1. So here it is 1, 1, 0, 1. When you add these two numbers, 1, 1 plus 0, 1, 1, 1. Okay, so the result is 1, 1, 1, 1. What does this mean? The carry, if you see, 1 plus 0 is 1. Here the carry is 0. Again 1 plus 0 is 1, the carry is 0. 1 plus 1 is 1 plus 0 is 1, the carry is 0. And here again the carry is 0. This is 0. The two carries, C3 and C4, are same. That means the result is correct. Now tell me, in the 2's complement representation, look at your table. Initially I told you to wrote. Look at that and tell me what is 1, 1, 1, 1 in signed 2's complement representation.
Minus 1.
Minus 1. Correct. Okay. So our result here is minus 1. 2 minus 3 is minus 1. Correct. So we got the correct result. So you can detect if there is a overflow or our result is correct or wrong. Okay. If there is a overflow, definitely the result will not be correct. Okay. You will be considering overflow bit with the result bit to find the correct result. Okay. Otherwise, when the carry is 0, okay, C3 is 0 and C4 is 0. That means there is no overflow, and this is 1, 1, 1 is 1, 4 ones is the representation of 2's complement representation of minus 1. Okay, this is how addition and subtraction on 2's complement data is performed. Okay, any doubt? Any doubt in this? We have seen the hardware implementation and the flow chart. Let me check the attendance. Okay, please join before the class, before the teaching start. Okay, once I start teaching, I'm waiting for some time, okay, for you all to enter. And once after 5 minutes, after 7 minutes only, I'm starting the class. So once I start, it will be difficult. But what I'm telling is join before the teaching starts. Okay, at least within 5 minutes, you can try to log in, join the meeting within 5 minutes. 10:15 it starts actually. I'm waiting till 10:20 and then starting. Every day I'm noting down the attendance. Okay, all the participants list, looking at the participants list, I'm noting down the attendance and it has been entered correctly. So there is no doubt if you have entered the meeting and you are staying till the end, okay, you will get attendance. And even initially, I will check it once so that we will get to know if somebody get disconnected and join back, I can note down the numbers and you will not miss your attendance. Okay, any doubts in this class from signed magnitude, addition and subtraction, and signed 2's complement, addition and subtraction. And the next class, we have other two operations, multiplication and division. Okay, addition and subtraction we learn together. Same way, we learn multiplication on signed magnitude data and signed 2's complement data, and then division. Okay, before that, you make sure that you understood this thing. Okay, addition and subtraction.